Have you ever heard the phrase, we know more about space than our own oceans? Well, that's a really hard statement to prove. It does bring up a good point about how little we know about the seabed. We've been mapping the seabed for decades, but we only have 24.9% of it mapped at an adequate resolution. With the climate crisis worsening daily, we don't have any time to waste. The sooner we can map the seabed, the sooner we can predict natural disasters, clean up ocean debris and pollution, farm more sustainably, and more. To complete the remaining 75% of the map before 2030, a goal set by Seabed 2030 to protect the planet and its residents, we can't just rely on human-operated boats. We must use AUVs and ASVs.
While these robots can make great paperweights, it takes elegant math and programming to bring them to life, enabling their collaboration to complete this map. For this, we look to the Traveling Salesman Problem. The classic example of this problem examines a salesman who must travel between a few specified cities. They must visit every city exactly once and return to their home city, taking the shortest route possible. Let's transform this into something relevant and fun. We'll transform the salesman into an AUV and the cities into points of interest that are not mapped at adequate resolution. The lines between each point, or edges, show that travel between those points is possible. The numbers on each edge, or weights, show the distance between those points in minutes of travel. While there are many ways to solve this problem, today we will focus on one.
Before we dive in, it's important to note that the Traveling Salesman Problem is in the class NP, which means that a computer can find you an answer, but no computer can reliably find you the best possible answer in a realistic amount of time, even on the world's fastest computer. Since this problem has remained unsolved since 1971, let's examine a useful and quick algorithm for this problem.
This is the cheapest link algorithm. It finds a path including all points on a complete graph by repeatedly picking the shortest edge, ensuring that no vertex has more than two edges coming out of it, and that there are no cycles that don't include all the vertices. This algorithm may not always find the best possible path, but it finds a short path very quickly, and with the enormous scale of the seabed, speed is our best friend.
Speaking of scale, let's take a break from theory and get some perspective. Right now I'm next to Lake Lanier, which covers about 39,000 acres. Imagine just how big the graph would have to be to map this. Now, let's zoom out and see how much of a challenge lies ahead.
From an overhead view, Lake Lanier looks massive, but it's nothing compared to the size of our oceans. Remember, we still have to map over 75% of all this blue.
Mapping the seabed is a daunting but vital task for the health and safety of our planet. The cheapest link algorithm is a start, but it will take unique perspectives and collaboration to finish this map by 2030. Whether or not you're in STEM, please become part of this global effort. Here are some ways that you can help.